What I'm interested in is the structure of solids, because if you can understand and control the way molecules pack to give solids, then you can control and manipulate and understand their properties. And so this has been one of the big fields in chemistry, maybe in the last 20 years, is learning to understand how molecules give a structure, give a crystal, and then using that understanding to manipulate the properties. And one of the ways to do it is to think about a crystal as a network of molecules. And if you think of them as a 1, 2 or 3 dimensional network, then you can use that same approach not only to understand it but to also design structures. So if you take a very simple network like the diamond network, so this is how the carbon atoms are arranged. I've got a model of it here. This is how the carbon atoms are arranged in diamond. If you can coax molecules to come together in the same arrangement by controlling the geometry of the molecules, then you can design structures. So you can take something that's like this, but if you use slightly longer links, okay, then you can start to make structures that have slightly bigger spaces. So you can see this is topologically the same. All I've done here is between my branching points I've got longer and longer distances. Okay, so for here, for example, instead of a carbon-carbon bond, I might have a molecule that's a tetrahedron, mix it with a metal that is a tetrahedron, and you end up with very long links, and these become quite long. Okay, and you can go from that, and you can take it even further. Here's a typical ligand bridging between molecules on the same sort of scale, and you can see you can get very big open spaces very quickly in a crystal. And so you can lead to all sorts of applications. Okay, this material here, for example, 60% or sorry, only a third of the crystal is the ordered space, and the rest is essentially liquid. And if you can take that liquid out, you've got something that's 80% or sorry, 70%, 60% porous. So this has been a very big field, and there are lots of different nets that you can target. So here, for example, are just some nets I've selected, not quite at random, but they're all got, if you look closely, a square planar centre, all connected together in different ways. Each are all topologically different, and so there's been a lot of interest in this. I've been on IUPAC committees, so this is the peak world chemistry body, looking at how we classify these net topologies and start to name them. And so that's included some of the leading people around the world, and also some of you may know Stephen Hyde, a mathematician at ANU. He's been involved in that as well. And certainly the chemistry world's, and Stephen's got his own versions of these databases, have set up databases describing these different topologies. But one of the consequences of designing structures like this, oh, sorry, this is just a picture of my office. You can see where these came from. Yes, I went a little bit overboard in the holidays. These are toys from Aldi. So I got some strange looks when I walked out of Aldi with 20 boxes of these kids' toys. Anyway, one of the consequences, however, of making things that have got very big spaces in them is that you can get multiple networks interpenetrating. Okay, so that the holes of one network, and I've got an example here, one network are taken up by the formation of a separate network inside it. Okay, and this is just an example, a fairly simple example with 2 diamond networks, and they're they're moving through this, well, not moving, they're occupying the spaces of each other, but they're not actually connected together. Okay, so a bit like links in a chain, except the links are 3-dimensional networks rather than discrete 0-dimensional finite things. And so this is a big challenge is to describe and understand the way these networks can interpenetrate, because they have a big effect on the properties. And so this is really what I'm interested in this context, is the way these networks interpenetrate. So we've come to an understanding, or we're working on understanding the topology of networks themselves, but there's also something else that I like to call the topology of interpenetration, is understanding the way networks can interpenetrate. So we have over the years, that's a very young looking me, a lot more hair, still not a lot. We have over the years written some reviews. I don't know if you can see, this one here's got nearly 4,000 citations, this one's got 800. I put those there just to give you the context of the sort of impact or the sort of interest in this sort of topology of interpenetration there is in the chemical world, in this framework world, because we need to understand the way these things interpenetrate. So in both of those reviews, we started to work our way towards trying to come up with a way of describing how the networks interpenetrate in different topological ways. So here, for example, are 3 different topologically different ways that simple, we call these 4-4 sheets, these are square grids, but these are all interpenetrating in 3 topologically different ways. If you look at this one, the rods are going through the red rings and the red rods are going through the blue rings. If we look at this one, you can see the node is sitting in the ring of the blue net and the blue node is sitting in the ring of the red net. Here you've got rods going through the rings in the red net, but the red net's nodes are sitting in the blue. Okay, so they're 3 topologically different. So the topology of the nets themselves is the same. They're all simple square grids, but they're all entangled or interpenetrating in 3 topologically different ways. So a little while ago we came up with a very crude first step in describing the different topologies of interpenetration. And it's really just, we describe the dimensions of the individual nets themselves, the dimension of the overall entanglement, and for 1 and 2 dimensional networks this can happen in either a parallel or an inclined way, and I'll show you this in a moment. So here, for example, here are 2 one-dimensional nets. These are just kind of one-dimensional ladders, and overall they're interpenetrating to give an overall one-dimensional entanglement. Okay, I know mathematicians probably prefer to call this periodic, but us chemists some of us chemists like to use dimension instead. 1-dimensional to 2-dimensional parallel entanglement. So again, as here, the mean directions of propagation of the nets are still all parallel, but here where they're probably coincident or very close to coincident, here they're offset, and you get an entanglement that's overall 2-dimensional instead of 1-dimensional. So there's still the topology of the nets is still the same. They're still all parallel to each other, but this is giving a 2-dimensional entanglement. You can go to, here's just a way of entangling 1-dimensional nets to get a 3-dimensional entanglement. Here's another way. This one I made up. This one is actually a real crystal structure. And again, these are, it's kind of a double ladder now, but these are 1-dimensional or periodic in 1 dimension, but they're giving an overall 3-dimensional entanglement. You can do there's another way. And this is the other way, is you can have inclined interpenetration. So instead of the nets all being parallel, they can be inclined to each other, and here we've got 1-dimensional nets interpenetrating to give a 3-dimensional entanglement. 2-dimensional nets can do the same sort of thing. Okay, so here are simple 2-dimensional nets. I've drawn the atoms in here, so I could have drawn this topologically, but here we have kind of undulating nets giving discrete layers or discrete 2-dimensional entanglement. Here are topologically the same layers, but because now they're offset but they're still parallel, it's giving a 3-dimensional entanglement. And again, with sheets you can have, as we saw right at the start, you can have inclined interpenetration of sheets. If you're interested in topology, you probably know about Borromean rings. Borromean rings are a curious little thing where if you take the rings are entangled, but if you take any one of these rings out, the other 2 are no longer entangled. So if I take this red one out, for example, then the yellow and the blue one you can now separate without having to break bonds or whatever you mathematicians call them. You can have Borromean type interpenetration in polymeric networks. Okay, so again here is a 2D to 2D parallel entanglement. So these are two-dimensional sheets giving a two-dimensional entanglement. But if I take out any one of those sheets, I can't separate them, but if I take out one of those sheets, I can separate the other two without having to break any bonds. So it's just a polymeric analogue, if you like, of the discrete rings. And of course you can have three-dimensional entanglement. So there was the one I saw before. And this can get quite extreme. This is the world record holder. And when my collaborator sent me to this, my first reaction was, what a load of rubbish. You've obviously done something wrong. And then the more and more I looked at it, the more and more they were right. But we have a fairly simple network here, but there's 54 of those networks interpenetrating in this crystal structure. Now this is a real crystal structure. It has 54 networks, all separate, but all interpenetrating each other, which I still find amazing. And sorry? What crystal? There's the reference. Silver and a big long ligand. I can't remember what it was now. And that was 3 times the previous record holder, and nothing else has come close to it since. And trust me, there were a lot of headaches in trying to work this out. You can also have weird things like networks, different networks interpenetrating. So here is one-dimensional network interpenetrating with a three-dimensional network. Here are 2 diamond networks interpenetrating with a niobium oxide net, or NBO net we call them. Yeah, and I mean, you know, it's just fascinating how it manages to fit everything in, particularly with such regular geometry. You can also have chiral networks. So if you look closely, you can see these are spiraling clockwise into the board. You've also got the opposite handedness where it spirals into the board anti-clockwise. But these can interpenetrate such that all the nets are the same handedness, I'm going to guess. No, I'm guessing that's the same handedness one. Or you can have them where they're the opposite handedness. So, the challenge really for us, and I should say this is not really, I mean this is a little bit different to the last 2 talks in that this is not so much a specific problem or a finite problem that we're trying to solve. This is really something that I'm surprised mathematicians are not all over much more than they are. And maybe that might be my ignorance, maybe you guys are. But this is sort of something that, you know, if I was a mathematician or, you know, a topologist, I could quite happily spend 20 or 30 years playing around with these systems, because there's a really an amazing amount of, you know, the more you look at these systems, the more you see, and the more the different ways these things can interpenetrate. You know, it's really not so much a problem as I think it's a field of overlap between maths and chemistry that I think has really got a lot of potential. And as chemists, we're really only scratching the surface. And you know, as chemists, we're trying to solve these problems as we see them in crystal structures and trying to work backwards, kind of thing. But the question really is, you know, one of the questions that we're trying to solve around this is, how do we, apart from showing a damn picture, how do we describe why these are different? You know, and how do we categorise these as different, apart from the very crude categorisation of, you know, 1D to 2D to 3D that we've come up with so far. And there's not really a lot of people looking at this. That's interesting. I will hang up on my wife. I will get in trouble for that. Yeah, note from the head. I've lost complete track of where I was now. Yeah, so you know, people are not looking at this, and you know, we've kind of looked at it in a little bit over the years. There's a joint Italian-Russian group. which is going into it a little bit more and trying to describe them in terms of topology of Hopf links and things like that. But apart from that, that's it. And it really strikes me as something where there's a rich kind of mathematical topology field that just to play on, I think, which is really interesting. I'll just give a couple more examples. Here's another example. It gets even more complicated. So here we've got two sets of sheets interpenetrating an inclined angle. Here we've got four sets of sheets interpenetrating at different angles. So we've got the red ones, we've got the blue ones, we've got the yellow going this way, and we've got the purple going that way. I mean, firstly, how these things miss each other is remarkable. Again, this is a real crystal structure. But again, you know, how is that different to the next one that comes along, other than just drawing it and looking at it and looking at it and looking at it and looking at it until you can see that if it is different or not. Even simple planar sheets you can interpenetrate differently. I'll skip over that. Three-dimensional ones. I'll finish just with an example that I'll take you through. If I come back to the diamond network, so here are two interpenetrating diamond networks, and the characteristic of the diamond topology is this, what we chemists call this adamantane cage. And you can describe a relationship, or you can attempt to describe a relationship between the interpenetrating cavities of one. If you pick out one and you pick one of the hexagonal rings, and then you choose the rod that penetrates it from the other network, and then you use that internal one to define the rest of your adamantane of the second network, then I think we have a unique relationship between the two networks. And so that's a very common, almost all the interpenetrating diamond networks show that sort of interpenetration topology. But the key word there is almost. And there are some really curious exceptions. So here, for example, are five different interpenetrating structure that has five different interpenetrating networks. Each pair of networks in that structure has that same relationship that I just showed you. Has that particular relationship. But here's one, and don't try and understand that, it still gives me headaches, but here's the structure that we did here at Monash 10, 15 years ago. But let's draw that same relationship that I just showed you for these. Okay, so I'm going to choose this network, and it didn't matter which one I choose because they're all crystallographically related. So there is, topologically, there is only one network and it's related to the rest of them. I'll choose this ring here. Here's my rod coming through it, and then there in the rest of red is that adamantane unit, the unique adamantane unit that I've generated from it. And so it has this relationship. Each one of these six-membered rings has a rod going through it. Okay, so that's between nets 1 and 2. Between nets 1 and 3, it's the same. The geometry is a little bit distorted, but again, in topology, the geometry doesn't matter. And that's one of the challenges as chemists, is separating that from the crystallographic symmetry is not trivial. So 1 and 3 are fine, but what happens in 1 and 4? Okay, again, here's the rod going through, defining my adamantane unit from it. Notice this six-membered ring now no longer has a rod going through it. Okay? And then if I go to nets 1 and 5, again, in fact, this is not entangled at all. It goes through here and comes out the other side. Now remember, I've defined that uniquely based on this ring. So I can show you pictures and show you why it's different, but I can't put into, it's really difficult to mathematically describe how those topologies are different. And particularly easily, because this is quite tedious going through each one of them and checking and working it out. So that's really where I think there's an opportunity for people interested in topology, that there's a very fertile field here that you can play around with. And I think that's it.